Welcome to the Tutte Colloquia. We're very glad to have Felix Leditzky speaking today. Felix finished his PhD in 2016 at the University of Cambridge, and followed by a postdoc at GILA at UC Boulder with Graham Smith, and since December 2019 has been a postdoctoral fellow at IQC and the Perimeter Institute. Felix's research spans a wide range of topics in quantum computing and quantum information theory, and today he will tell us about symmetries and asymptotics of port-based teleportation. Felix.
Thanks a lot, David. Hi, everyone. Thanks for coming. And thanks for giving me the chance to present my work at this colloquium and to talk about one of my favorite topics in quantum information, which is port-based teleportation. And in particular, I want to tell you about the symmetries and the asymptotics of port-based teleportation and how we can use representation theory to derive those. So part of this talk is based on a paper that appeared 2 years ago and is joint work with Matthias Christandl, Christian Mayens, Graham Smith, Florian Spillmann, and Michael Walter. And part of the talk is also on unpublished work, which you will see later. So teleportation is, in my opinion, one of the most fascinating applications of using entanglement in quantum information processing. So in order to understand what teleportation is, we need to understand what entanglement is. And I chose to let one of our founding figures in the field explain to you what entanglement is. So Charlie Bennett, who received the Shannon Award this year, describes entanglement in the following way: an entangled state describes the complete knowledge of the whole without knowing the state of any one part. I will make this a little more precise later on, but for now, just think of entanglement as a strong form of non-local correlation between separated quantum systems. And it turns out that we can use these non-local correlations to do incredibly useful things in quantum information processing. But what we usually need with entanglement is that we need some other resource that we use together with entanglement to do something useful with it. And this was first realized in one of the breakthrough results of our field in '93, which introduced quantum teleportation, where Charlie Bennett, together with his colleagues, so we have here Richard Josa, Bill Wooters, Charlie Bennett, Gilles Brassard, Claude Crépeau, and Asher Paris. And these people realized that you can use the correlation in an entangled state together with classical communication to teleport an unknown quantum state from one lab to another distant lab. And the goal of this talk will be to study teleportation and introduce to you a certain variant of teleportation called port-based teleportation, which has very nice symmetry properties. Okay, so this is the outline of the talk. Before I go into the actual content, I need to have two boring slides with quantum information terminology, so that we're all on the same page. And then once I have that out of the way, I can talk about port-based teleportation, define it and tell you some of the nice properties it has. I will then go on to describe the symmetries of port-based teleportation and how we can use them to characterize port-based teleportation protocols. Then in a second step, I want to talk about the asymptotics of port-based teleportation. So what can we do, what can we say about some suitable asymptotic limit, which I will explain later. And then I'll conclude with some generalizations and concluding remarks. Okay, so quantum information 101. In quantum information, when we talk about quantum systems, we usually model them with Hilbert spaces. And in this talk, everything will be finite dimensional. So we talk about finite dimensional Hilbert spaces. And then a quantum system is described by a quantum state. And a pure state is identified with a normalized vector in this Hilbert space. And for all the mathematicians, I'm using the bracket notation introduced by Dirac. So these kets, which are these like right-pointing things, denote vectors in the Hilbert space. And the bras, which are the left-pointing things, denote the Hermitian adjoint of these vectors, which live in the dual space. So pure states are just normalized vectors in this Hilbert space that models our quantum system. Now a mixed state is a probabilistic mixture of pure states, which kind of reflects our lack of knowledge of what state the system is prepared in. More mathematically speaking, we can say that a mixed state is described by a linear positive semi-definite operator with unit trace. And if we talk about multiple quantum systems or a big quantum system with multiple constituents, then we talk about tensor product spaces. So these quantum systems, let's say AB for a bipartite system, live on a tensor product space HA tensor HB. And then we want to talk about the states on this tensor product space, and then we will call a state entangled if it cannot be written as a product state. So this is the characterization for pure entangled states. For mixed entangled states, you can say that every state that is not in the Comex-Halldorf of product states is called entangled. And one prototypical example of an entangled state is a so-called maximally entangled state, for which you can, for example, take two-level quantum systems, for example, the spin of an electron. And a spin can be up or down. Those are the two kind of like basis states, also called 0 and 1. And then for the maximally entangled state, what we do is we take the state where both spins point upwards, and then we put it in superposition with the state where both spins point downwards. And in the future, for all the diagrams, when I write like these two balls with this squiggly line in between, I will mean this maximally entangled state. And there's also a nice generalization to D-level systems where you take a superposition over all tensor products of the D basis states. And when we have composite quantum systems, we want to talk about the global state of that quantum system, but we also want to talk about the marginal states, which is the state that each lab or each quantum system individually sees. And to obtain the marginal state from the big global state, what we do is we use the partial trace operation to obtain the marginal state of our quantum system. The partial trace operation mathematically is a unique operation that satisfies this relation here, which is just to say that if you have an observable XA that only acts on the A part, then the expectation value for that observable is just given by the marginal state. And this is defined to be the partial trace of the global state. So this should hold for all Hermitian observables XA. And if you do this partial trace operation with this maximally entangled state that I've written here above, then you'll find that the two marginal states on A and B are completely mixed for this maximally entangled state. Or in other words, while the global state is in a defined state, the two marginal states look completely random to the observers Alice and Bob. And so remember Charlie's words, an entangled state describes a complete knowledge of the whole without knowing the state of any one part. This is exactly the mathematical characterization of this nice statement of Charlie. Okay, now that I have this out of the way, and I hope everyone is on the same page about this quantum information terminology, I want to talk about porpoise teleportation. But first, I want to spend a little more time explaining to you how the standard teleportation protocol by Bennett et al. Works. So the idea of teleportation is you have this entangled shared state between Alice and Bob, and you also have some classical channel that they can use. So Alice can call Bob and tell him some message, some classical message. And the idea for teleportation is now that if you combine the entanglement and the classical channel, you get a quantum channel. So Alice and Bob have this entangled state between them. They have this classical channel between them. And then Alice has an additional qubit C, say, that she wants to teleport to Bob. And the way the teleportation protocol works now is that Alice does a measurement on the qubits in her possession. So she measures C and A1. A1 is the half of the entangled state that she has. And the idea is now that this measurement through the entanglement with Bob kind of steers Bob's state into something that looks like the state that Alice wants to teleport. It's somehow a rotated version of this. And the point is now that with the knowledge of the outcome that Alice gets from the measurement, she can actually tell Bob how to correct this rotated form into the actual state that they want to teleport. So the protocol works like that. Alice measures her qubits. She gets some outcome. She tells Bob the outcome through this classical channel. And then conditioned on that outcome, once Bob learns that, he can apply a correction operation to his half of the entangled state, such that as a result, he will have this unknown state C in his lab. And so it has been teleported from Alice to Bob. And one thing that porpoise teleportation tries to address is the fact that here in the third step, when Bob needs to correct his system based on the classical information of Alice, we want to make this correction operation as simple as possible. And so this naturally leads to port-based teleportation, which is now a situation where Alice again wants to teleport some unknown state in a qubit C to Bob. But instead of just one entangled state, let's assume that they have n entangled states between them. Okay, so we have these n maximal entangled states here on A1, B1, A2, B2, etc. Alice possesses the A systems and Bob possesses the B systems. And they again have this classical channel between them. And the teleportation protocol now works in a similar way. So Alice again does a measurement on her qubits, which is now n plus 1 qubits, the NA ports and the C qubit. And she will again get some outcome from this measurement that she tells Bob. And then based on this classical message from Alice, Bob now needs to decide which port system should hold the teleported state. But the point is now that the only correction for Bob is to select the right port. He doesn't need to apply any unitary rotation anymore to that qubit. So this is where this deviates from the standard teleportation protocol. And so, for example, in the case that it's the second port that holds the state, then Bob will just discard every other port but the second one. And then the B2 system will hold some approximate copy of the target state. And the nice thing about this way of implementing the teleportation protocol is that this correction operation that Bob does, this tracing out everything but one system, is very easy and simple, and it actually commutes with any unitary that you apply to each of the port systems. So the protocol works in exactly the same way if Bob, before starting the protocol, just applies the same unitary to all of his B systems, to all of his ports. And as an effect, when Alice and Bob run through the steps of the teleportation protocol, they will now not teleport the state psi that Alice started with, but they will teleport the state psi where you have applied the unitary to it, which turns out to be very useful in applications, but there is a downside to this. There is a very old result by Nielsen and Chuang that says that any protocol that does this, that kind of teleports a state to which you apply an arbitrary unitary, this cannot be perfect if you have finite resources. Finite resources meaning here that you have a finite number of ports. So while we gain this property of unitary covariance, which is incredibly useful, we kind of lose something as well by turning this teleportation protocol into an approximate protocol, which is not perfect anymore. But nevertheless, this unitary covariance is so useful and important that it enables a couple of applications of port-based teleportation. So the one that I just mentioned to you that kind of leads to this no-go theorem is that you can implement universal programmable quantum processors with it. Another important application is in cryptography, where port-based teleportation provides an attack on something called position-based cryptography. Then it had also been used in quantum channel discrimination. And right now, with some colleagues at IQC and Perimeter, we're trying to figure out what the connection between port-based teleportation and entanglement-assisted quantum error correction is. So these are some applications. I hope I convinced you that port-based teleportation is somewhat interesting task to look at, and I will now take for granted that it's important and useful and interesting, and I will only talk about the characterization of port-based teleportation. Okay, is there a question right now that I can answer?
So Felix, why did you say apply the same unitary on each of the port? I mean, they're free to apply any unitary, right? I mean, any tensor product unitary.
Yes, but for the total channel to be unitarily covariant in the strict sense, you need to have the same unitary applied to every state.
When you say channel, you mean also tracing out operation. You want to include that?
Yeah.
Okay, cool.
Yeah, exactly.
Question? So
Yes.
do I think of the measurement as having an outcome that gives me one of those AI systems at random, that gives Alice one of those systems at random?
I will in one or two slides. I will say what that measurement is actually doing.
Gotcha.
So bear with me for one or two slides.
All right, thanks.
Okay, I'll continue if there are no further questions right now. So So we have this no-go theorem because of this unitary covariance that purpose separation cannot be perfect. So what we now need to do is we need to, or what we want to say is, how good is it? How faithful is this protocol that I can implement using n ports and some measurement? And you can rephrase this question by saying that the port-based teleportation protocol implements a channel where you want to teleport. So the channel has as input the system C, which holds the state that you want to teleport, and teleports it into one of these ports BI, which I call C prime. Okay, and then what I do is I look at the channel from C to C prime, and this is called the teleportation channel. And then we ask, how close is this channel to that identity channel? So how good is the approximation that I make in this teleportation protocol? And one way to measure how close the channel is to the identity is by means of the so-called entanglement fidelity, where we ask, how well does this channel preserve 1/2 of a maximally entangled state? So what I do is I start with, I put the qubit C to be teleported into a maximally entangled state with some reference system C double prime. And then I send the C through the teleportation channel. And then I measure how much of this entanglement in the initial entangled state did I preserve using the channel. And the closer this quantity is to 1, the better the channel is. And it's equal to 1 exact if and only if it's an identity channel, if there's no noise in the game. So this will be our main figure of merit to judge the quality of a port-based teleportation protocol. And so now I can answer John's question from before. So port-based teleportation was introduced by 2 Japanese researchers called Ishizaka and Hiroshima in 2008. And the crucial fundamental insight that they had is that the task of teleporting 1/2 of a maximally entangled state through these ports is equivalent to the task of discriminating a certain set of states. And these states are given by these color shades here. I tried to draw this and I hope this is somehow clear. So what Alice basically has to do is she has to distinguish her NA ports plus 1 of Bob's ports. And the other ones are traced out. So kind of Alice needs to distinguish, is my first system entangled with Bob, or is my second system entangled with Bob, and et cetera, et cetera. And it turns out that if you put a uniform prior probability on all of these states, and we have n states, so this is a uniform prior of 1/n, then, is there a question? No, okay. Then it turns out that teleporting an unknown quantum state is exactly equivalent for Alice to discriminate between those n states, in the sense that the entanglement fidelity of the teleportation channel is a simple function of the success probability of successfully discriminating these n states, eta 1 through eta n. And I've described here the situation where we have n maximally entangled states between Alice and Bob, but this connection between port-based teleportation and state discrimination actually holds for arbitrary port states between Alice and Bob that are not necessarily of the form n entangled state and maximally entangled states. Okay, and the nice thing about this connection between port-based teleportation and state discrimination is now that we can use the machinery for state discrimination. And the nice thing about this is that there is a nice formulation of state discrimination in terms of semi-definite programming, which is a nice class of convex optimization problems. So the state discrimination problem is, I give you n states with some prior probabilities, and you need to make a measurement and tell me what state I gave you. And so the primer problem is just to maximize this success probability, which says that on average, you guess the right state, weighted by the probabilities with which I draw the states. And the measurement here is described by certain positive semi-definite operators EI, 1 for each state that you want to distinguish. And the fact that it's supposed to be a measurement is the requirement that the sum of all of these measurement operators EI is the identity on the full Hilbert space. Okay, so this constitutes the most general quantum measurement. It's also called a POBM here. And so this is kind of the primal problem in the semi-definite programming picture, where we maximize this success probability. And then for every semi-definite program, you can go to the dual problem, where you turn the maximization into a minimization. And it's an easy exercise to deduce the dual problem for state discrimination, which is to find a certain
There wasn't
operator.
any.
Is there a question? No, okay, someone's just not muted, I think. So the dual problem is to find an operator K whose trace we want to minimize. And the subject is that in the operator order, in the positive semi-definite order, this K should be larger than the probability of the ith state times the state for each I. So for each state, this needs to hold. And semi-definite programming has a nice duality theory, and there's something called strong duality where the values for the primal and the dual problem are actually equal, which is the case here. And so the success probability is obtained by solving either one of these problems. And we're going to use both in determining the optimal entanglement fidelity. Okay, so we have now this semi-definite programming picture for state discrimination. Applied to our case, we have this port state consisting of n maximally entangled states. So this is just n tensor copies of the state phi plus that I showed you before. And the state discrimination problem is now to distinguish between these states eta I, where eta I consists of the maximal entangled state between AI and BI, and the maximally mixed state on all the other A systems. Remember I told you when in the maximal entangled state, when you trace out one of the systems, then the resulting marginal is completely mixed. And so these are the other halves of the maximal entangled states here. And the uniform probability on these states is 1/n, because we have n states to distinguish. And now a natural question is now, what's a good choice for the PUVM? What's a good choice for this measurement? And it turns out that we can make a pretty good choice, which is the pretty good measurement. And to define that, what we do is we take the average state. So we take each state, weighed by the probability, and then we take the sum. And then we form measurement operators EI, where we sandwich a state with its weight by 1 over square root of this average state. So this is the reason why sometimes, and I think in the mathematical literature, it's more usually called square root measurement, because here you have these square roots appearing. And it's easy to check that because we have here quantum states, which are positive semi-definite, that these measurement operators are also positive semi-definite as required. And they sum to the support of the average state, which might seem like a problem, but like if you have a state discrimination problem, you can always restrict your Hilbert space just to the support of eta, so that this is actually the identity on the full space. And then you have the normalization requirement that I showed you before for these measurement operators. And we will see later that the pretty good measurement, it's called like that because there's some task for which it does a pretty good job. So it's kind of like close to optimal, and you can say how optimal it is. It turns out that for port-based teleportation with n maximal entangled states is actually optimal. So we will prove this later using semi-definite programming duality. Okay. So now that I've set up port-based teleportation and the connection to state discrimination, I can talk about the symmetries of port-based teleportation, which is a big topic. And in order to understand teleportation, all we really need to know is this kind of fundamental symmetry that the maximally entangled state has, where so the maximal entangled state is a bipartite state. And if you take some unitary u and you act with u on the first system and the conjugate, complex conjugate u on the second system, then the maximal entanglement is invariant under this operation. Okay. And now, since the states that we have to discriminate are basically these maximal unitaries trivially as a symmetry, then this u tensor u star symmetry now translates to a symmetry for these states eta I. Okay, so I tried to draw a picture here where this is the.
I have a question.
Sure.
If my dog all live on the same Hilbert space because they're phi plus on AI, BI, and then you put the identity for Alice, but what about for Bob? You just left out completely.
Right. So I should have said that, and I think I said on a later slide. The BI is actually here taken to be the A1, B1 system, we have the U tensor U star symmetry coming from this fundamental symmetry. And then the other ones are just identity or proportional to the identity. So we have, trivially, we have a U symmetry. Yeah. And we also have a permutation symmetry. If I permute the other A systems, nothing happens to the state. So if I take together the U tensor n-1 invariant,
Are eta I the only states that satisfy this two equation that you wrote?
No.
Okay.
No, it's so I will come back to the point later when we like look at the representation theoretic description of these states, and then you have some wiggle room there. These are not the only states. Yeah. Okay. So I have the symmetry for the individual eta I states, and remember, in a pretty good measurement, what also appears is this average state, where I sum over all the etas. And what symmetries does this state have? So we again have the U tensor U star symmetry coming from the maximal entangled states, but since I now sum up over all of these maximal entangled states, I actually have it on every pair of qubits. And furthermore, I now have a full permutation symmetry, because now all of the A systems are on equal footing, because I sum over all the states where one of them is connected to Bob's system. So in addition to the U tensor n tensor U star symmetry, I now have a full SN invariance, which is the second relation here. So I have two symmetries, one for the eta, I have the individual eta states with two symmetries, and then I have the average state with another two symmetries, and the question is now how we can relate them. And in order to do this, I want to take a step back and describe in more generality what kind of symmetries we're talking about here. So we look at states on the representation space CD tensor n. So I have a d-dimensional Hilbert space, and I take n tensor copies of this. And then there are two very natural representations on this space. One is the representation for the symmetric group, where the symmetric group acts by permuting the tensor factors. So I again try to draw a picture. So in the first step, I have the symmetric group acting on the tensor factors by just permuting them. And then on the other hand, I have a representation of the unitary group acting by diagonal, like using the diagonal action, where the same unitary acts on each tensor factor. Okay, so the same unitary U acts on each tensor factor individually. And from the picture, it's kind of clear that the two representations commute with each other. It doesn't matter which one I apply first. But what's more is that not only do they commute with each other, they actually span each other's commutant, which is very nice, because that means using kind of like basic representation theory, that the representation space now decomposes nicely into irreps of Sn and Ud. This is called Schur-Weyl duality. In order to state Schur-Weyl duality, we need to fix some terminology. So it's kind of a well-known classical representation theory result that the irreps of the symmetric group and the unitary group are indexed by Young diagrams, which you can in turn identify with partitions of n. So a partition is a collection of numbers that sum to n, and we will take them to be non-increasing. And then you can arrange them in a diagram where for each mu I, you take I boxes, and then you come up with this diagram here. And now the non-increasing requirement means that the length of the rows should be non-increasing. And then each one of these Young diagrams now labels an irrep of Sn, and the corresponding representation space is called the Specht module, W mu. And I will denote the dimension of this module by d mu. And on the other hand, the irreps of the unitary group are live on the Weyl modules V mu D, which also depend on the D here, on the local dimension of the Hilbert spaces. And one more notation is what we do here when you talk about Schur-Weyl duality, you only consider partitions into at most D parts, which means that in the Young diagram you have at most D rows, where D is the local dimension of the Hilbert space. Okay, and with these definitions in hand, we can now talk. Or right, when the representation space CD tensor n. Tensor, sorry, U star tensor U tensor n symmetry, where the U star comes from the maximal entangled state and its symmetries. So the goal is now to incorporate this additional kind of representation, or this like by enlarging this space to this one additional factor, and then we have the U star tensor U tensor n symmetry, and we want to incorporate this into the Schur-Weyl decomposition, and this is done using the Pierre rule, which is also a classic result in representation theory. And it tells us that if so the U star is described by the dual representation. So we take the dual space of CD, which is isomorphic to CD, of course, and then we tensor it with the existing representation that we have on the n factors of CD. And then it tells us that the Pierre rule tells us that we obtain a representation that is not irreducible anymore, but we can decompose it into irreps again in the following way, where for each Young diagram, we subtract a box from a row where we can do that, in the sense that if I have a row for which is strictly longer than the next row, we can subtract a box from this row, which is what I mean here by mu minus epsilon I. And then has this U tensor n tensor U star symmetry, and then we can now decompose the state into a block diagonal form, where we need to apply this Pierre rule, and the result looks like this. So we have now these coefficients S mu alpha, and I take a Young diagram mu for n, and then I ask where can I remove a box. This will give me a new set of Young diagrams alpha, one for each mu, like one collection for each mu, and then this is how I get the resulting block decomposition. Okay. And we want to use this now to solve the state discrimination problem, which at first just means that we have our states that we want to discriminate. We have the pretty good measurement given by these measurement operators here in terms of the average state and the states. And we want to compute this expression for the success probability, where the PIs here are always equal to 1 over n. Sorry, I could have corrected this. And if we write things out, then we see that this operator ei eta I, for which I need to take the trace, is given by this object here. And now we use, I'm not actually doing this calculation here because it's kind of straightforward, but we can just use the symmetries and this special block diagonal form that I showed you before to compute this trace for this symmetric object here. And the ingredients for doing this are the symmetries and the resulting form using Schur-Weyl duality and this Pierre rule. And what we end up with is this beautiful formula for the success probability in the state discrimination task, in terms of representation theoretic data. So what we have here is we have a sum over Young diagrams on n-1, which I always call alpha in this talk. And then we take, we ask in what row can I add a box? And then I get a new Young diagram mu, which is now a Young diagram on n boxes. And then I evaluate this expression here, which is defined in terms of the dimensions of the two irreps. And this is the dimension of the Weyl module. This is the dimension of the spec module. And so this formula was derived by Studziński et al. In a very nice series of papers. But one thing that they actually left out to say is whether this is the optimal expression. So remember, we started out with saying that we have these n in maximal entanglement. Choose a pretty good measurement because it does a pretty good job somehow from like past results. But now we want to know, is this actually optimal? And the answer is yes, it is optimal. And one kind of straightforward way to show this is using the SDP duality that I showed you before. So remember, the success probability can also be expressed in this dual form, where we minimize the trace of a certain operator k that satisfies this operator order, partial order relation. And what we do now is we make a guess for this operator k, which has the same value as the success probability we just derived. So it turns out if you take for k this operator here, which looks a little weird at first, but it's kind of just the positive semi-definite version of pretty good measurement operator times state. And if we can show that this is feasible, meaning that this relation here is satisfied for each state, then we have shown optimality, because by construction, the two values for primal and dual program coincide. And so this is again kind of like a straightforward computation that I will not show you here, but it's again possible using the nice form that the eta I and the bar eta states have, using the symmetries that we have in porpoise interpretation.
A question? The general state discrimination problem?
I'm not sure I understand the question.
Well, this optimality that you show of PGM, why can't you show the same optimality for general state discrimination problem?
Oh, well, there are situations in which the pretty good measurement is also optimal for other collections of states, but it's definitely not optimal in a generic sense.
So your technique here only applies to port-based protocols.
The technique of showing that it's optimal, yes. I mean, the kind of the symmetry considerations also apply in a more general case, and I will say a little bit about this at the end of the talk. But here we have a really special kind of problem setup where we have these we have equal probabilities for all the states, and the states are just maximal entangled state times identity on the other systems. So this is a very, very special case of state discrimination.
Okay, thanks.
Right. Okay, I see that I'm getting closer to the end of the talk, so hopefully I can talk about the last kind of important chapter, which is to determine the asymptotics of porpoise teleportation performance. So we have now in this very nice work by Studziński et al. We have these beautiful closed formulas for the entanglement fidelity of porpoise teleportation, and it's closed, and it's given in terms of representation theoretic data. It's given by the dimensions of the irreps of the Sn and U action. But what's not so nice about these formulas is that it's very hard to see what happens when you have a large number of ports. And for example, you keep the dimension fixed, the local dimension. So this is kind of the asymptotic limit that we will be interested in this talk, that we keep the local dimension fixed but arbitrary, and it doesn't have to be qubits, it can be any qubit. And then we add ports. What does the entanglement fidelity do? And in order to understand these asymptotics, let's take another look at Schur-Weyl duality, and remember that Schur-Weyl duality gives us this decomposition of the tensor product space into a direct sum of these irreps. And now let's look at the projection onto one of these sectors. So we have a projection P mu, where mu is some Young diagram with at most d rows. And then the P mu projects onto this tensor space V mu tensor W mu. And since this is a projection or a resolution of identity, I can turn this into a probability distribution. If I just divide by the total dimension of the space, d to the n, what I get is a probability distribution, which is called the Schur-Weyl distribution, which explicitly is given by these two dimensions of the Weyl module and the Specht module divided by the total dimension of the space. And if I now take a random variable with values in the Young diagrams, whose distribution is the Schur-Weyl distribution, then a nice application of spectrum estimation tells me that this random variable, if I normalize by the number of boxes, if I normalize by the number of tensor factors, then this will, the average length of the rows will just converge to the uniform distribution, 1 over d. Okay, so why do I call the spectrum estimation? The Schur-Weyl distribution is actually nothing but trying to measure the spectrum of the completely mixed state. Okay, and spectrum estimation actually works more generally when you have some state, not necessarily completely mixed. But here we apply it to the completely mixed state, and then we get from this spectrum estimation results by Leditzky and Karl and Werner that this random variable, if I normalize by the number of tensor factors, converges to the spectrum, which for the completely mixed state is just a uniform distribution. And if I understand the spectrum estimation result as a law of large numbers, then I can ask what's the corresponding central limit theorem to this. So I want to look at the fluctuations of this convergence in a sense. So in order to do so, what we do is we take this random variable with values in the Young diagram. Central limit theorem tells me that the fluctuations of the Young diagrams behave like the spectrum of a matrix drawn from this ensemble. And the idea now to use this connection between Young diagrams and the GUE ensemble is that we have this entanglement fidelity expression in terms of the dimensions of the irreps. And the idea is now that we can rewrite this as an expectation value of a certain function small f in terms of these Young diagrams alpha on n-1 boxes. And then the idea is that once I manage to do this rewriting, I can now use the central limit theorem to, instead of compute things in terms of the Young diagrams, I compute things in terms of the spectrum of these GOE matrices, which is the only problem is that the result by Johansson only gives me the convergence in distribution. And what we need here is a somewhat stronger form of convergence of expectation values for suitable functions, f. And this is kind of in one slide, the main technical result of our paper, where we determine a class of functions f for which this convergence can be strengthened. And this class of functions includes the ones that you get when you rewrite this entanglement fidelity in a suitable way. And so once we apply this kind of stronger convergence result, we can compute this formula for the eigenvalues of a GUE, of a traceless GUE matrix. And then what we get is this very nice asymptotic behavior of the entanglement fidelity, where it converges to 1 in the limit n to infinity. So that was known before. We didn't derive this. But what we did derive is kind of the first order coefficient of this convergence. So we proved that this convergence happens in 1 over n, and the prefactor is given by the local dimension of the port systems, and the prefactor is d squared minus 1 over 4. And then we also have an estimate for the next order in this series. Okay. And to conclude, I want to quickly mention kind of the more general setting of purpose teleportation. So remember, in the very beginning, the way I set things up is that we said Alice and Bob share n maximal entangled states. They use pretty good measurement. We actually showed that a pretty good measurement is optimal. And then we get a certain asymptotic behavior of 1 minus 1 over n for the entanglement fidelity. Now, a natural question is what happens when you try to optimize over the port state that you start with? And in particular, can you achieve a better convergence for the entanglement fidelity in the number of ports? And the answer is yes, you can. When you optimize over these states and then also over the measurements, it turns out that you can achieve actually a scaling of 1. That you have the same symmetries is more general setting than the ones that you have that I showed you when you start with n maximal entangled states. So what Christian Mayens proved in his PhD thesis, and then we have a kind of more general treatment of this in our paper, is that when you take an arbitrary purpose teleportation protocol with some weird state, which I tried to kind of visually represent here, you can always symmetrize the protocol so that the new protocol has the same entanglement fidelity or better than the one that you started with. But now you actually have these nice symmetries. So you again have the permutation symmetry on each side of the ports. And you have this U tensor U star symmetry on each port. So you can again think of it as kind of maximum entangled states, but it can be something more general. And then this again gives way to a nice characterization of this optimal entanglement fidelity in terms of representation theoretic data, which was again derived by Michal Socinski and Marek in a follow-up paper. And then we again determined the asymptotics of this more general setting in our paper. And there's also maybe one thing I want to mention here is that there's this is something I'm working on right now, is there's also kind of like a more straightforward way to show this more general setting with just the tools that we developed, which is Schur-Weyl decomposition and Pierre rule. So this is work in progress. Okay, so let me conclude. We talked about porpoise teleportation, which is an approximate teleportation scheme. It has a very nice property called unitary covariance that enables interesting application. To use representation theory to characterize that have similar symmetries. So the permutation symmetry and the unitary symmetry are very common in quantum information, and hopefully our tools of strengthening this convergence in uations result will also be useful in other tasks. And with that, I'd like to conclude. Thanks.
Okay, let's thank Felix for a very interesting talk. So now we have time for questions. So if you have a question, please just unmute and interject.
I have a question.
Hey, John.
Felix, so on your last slide, these where you optimize over the port states, do you have a sense of what distribution that might be converging to instead of the GUE like for the other one?
No. So that's kind of when in this statement here, we are not convergence result where it converges. Only have a general
Okay.
And it's kind of we tried hard to find a bit more structure in this, but we weren't able to so far. So this is a nice open question to understand what's going on.
Cool, thanks.
I have a question on this slide as well. Can I ask?
Mm-hmm.
So what is the dimensional dependence on the fidelity?
In the fully optimal case?
Mm-hmm.
So the lower kind of is the thing in the
earlier result, you have d squared over n, which makes a lot of sense because we know that the
interesting. Yeah. Just open
If there's one other question, we have time for one more before the virtual grad house. If not, let's thank Felix again for a nice talk. And at this time, I'll stop the recording.